Hello everybody, I'm back again to talk about solution properties, physical properties of solutions. We're going to talk now about colligative effects, colligative properties, which start approximately on page 11 of the unworked out note sets for notes 13, physical properties of solutions, if you care to read along. So colligative properties have a lot of application. They're important for biology, they're important for environmental science. These will affect things like boiling point, melting point, as we'll talk about today, vapor pressure. And so colligative properties depend on the, I'll put a check here on the number of particles in solution. The particles, I'm using that term very broadly. They can be molecules or ions or even atoms in solution, so it's the numbers of particles. It's independent of the identity to a large extent. To a good approximation, it's independent of the identity of the particles, meaning if you have the same number of, let's say, ions of K plus and Cl minus in solution, let's say it's a KCl solution, and that's the same as, let's say, something that's, let's say, Na plus and bromide ions in solution. As long as there's the same number of particles in these two types of solution systems, you'll have similar colligative effects for things like boiling point, freezing point, and vapor pressure experiments. And similarly, if you have like molecules, like let's say you have something like some methanol in solution or some ethanol in solution, as long as you have similar numbers of these particles to each other, you end up turning out having similar colligative effects. So one of the ones I'm going to talk about today, get us going at least, is dealing with vapor pressure. So just as a review from last semester, you should have studied vapor pressure in towards the end of the semester. If you have, let's take a condensed phase. Let's focus on liquids. Let's say it's water and it's at a certain temperature. Let's just say 25 degrees Celsius, roughly room temperature. And what you'll find is that you'll have a certain equilibrium pressure of water in the gas phase, vapor gas molecules. Over it, you'll have a certain partial pressure. I'll just put pH2O. And again, that's a partial pressure. It's, the total pressure will obviously be a very minor contributor to the whole pressure. That's mainly going to be dominated by the molecules of nitrogen and oxygen and so forth. Over it, that whatever that number is, which I don't know off the top of my head what the vapor pressure of water is, 25 degrees Celsius, but it will be a characteristic we call the vapor pressure. When you have vapor pressure, it's a particular type of partial pressure. It's the vapor pressure between the gas that's in the liquid phase. Well, I'll just say this. Let's take water. The water in the liquid phase will be in equilibrium with the water in the gas phase. And the rate going forward, which we would call evaporation, and the rate, so this would be the rate of evaporation, and this going reverse be the rate of condensation, will be equal when you're at equilibrium, and that pressure that's exuded by the gas at that point, we call that partial pressure, the vapor pressure. Although some people call it the equilibrium vapor pressure, I really think that's a misnomer term because technically the vapor pressure is when you're at equilibrium. So you can put it in there if you like, but it's really an unnecessary term. So in this conversation, when I talk about vapor pressure, I'm meaning the pressure of the molecule associated with the liquid, its gas or vapor, over that liquid. This also is applicable to solid phases, the gas molecules over it, but we will not focus on that for now. So what we observe in nature is that, let's just talk about water right now. This is applicable to other solvents. Here's our little beaker with water. It's pure water. So we got a lot of water molecules swimming around here if you want to think of it like that. So this is pure water. What you'll find is, again, you'll have water molecules over it in the gas phase. Just we'll draw 3 of them just to give it that there's a few over it at a certain temperature. Let's just say at a certain temperature T. Whatever the temperature is, it is. Let's have another similar system at the same temperature. Let's just say it's room temperature, and you'll have water in there. Let's just say, for the sake of argument, a similar volume, similar shape container, just to make everything the same. And what you'll find is if you add solute particles to it, you make a solution. So this is no longer pure water, but it's an aqueous solution. Is that the vapor pressure decreases. So I'll just draw 2 gas molecules over it. So there's a decrease in vapor pressure when you have solute present, when you have an aqueous solution. And this holds for other solvents and their solutions as well. But let's just for now get the concept of it with water. Now the book has, I consider, inchoate or rather callow explanation of this effect. It says nature tends to mix. And because this system internally, it's all one thing, there's less of a tendency for it to mix, so it kind of disperses into the gas phase to allow it to have more ways of orienting itself. Where in here, it already has other components in there. It has the solute molecules that I'm denoting with an X. So there's less tendency of it for it to want to go to the gas phase. That's to me, kind of mumbo jumbo. We'll be able to put numbers to this type of phenomenon later, but let's get it straight. This is related to the idea, again, of entropy, which I'm going to denote with an S. Now this is FYI, but it's kind of important for the understanding, so let's just go through it really quick. You can just pay attention and get the gist of it. You do not have to reproduce this math. It's if you have had statistics and probability course, it would make sense. But let's just take the case where we have something like, let's see here, I want to draw a system. I'll just draw something really simple. Let's take 2 black balls. These black balls are identical and indistinguishable. I can't tell them apart. Just there's 4 grids. The grids are equal. You can only have 1 ball in there. This would be described by what we call binomial coefficient. We call it 4 choose 2, and this would come out mathematically to look like 4 factorial, 4 minus 2 factorial over the small number 2 factorial. If you do not know this, it's fine. I'm just getting a number out of this. This comes out to be 6. What you can do on your own is just verify there's 6 different ways of arranging those balls without having 2 balls in a slot in there. Now let's do something a little different. Let's take the case where we have 4 grids, 2 black balls, and 1 white ball. What this ends up being is a little different. Would be in mathematics what we call multinomial coefficient. Again, this is FYI in terms of the math. I just want you to get the concept here. And what happens here is, in this case, you have, this would look like 4 factorial, then there's 2 black balls, 2 factorial, 1 white ball, 1 factorial, which is just 1 blank space, 1 factorial. This is 4 times 3 times 2 times 1. These are all 1s. This is just a 2. That cancels that. 2, 6, 12. This is 12. There's twice as many ways that you can arrange this. Again, you can only have 1 ball per slot. The black balls are identical and distinguishable. The white ball is something else. It doubles up. So this would kind of be like the case of water. Let's just make water black dots. And the white dots being the solute particles, whatever they are, methanol particles, they could be ions. And so what you see is there's still some in the gas phase of this, but it already has a lot of more ways it can exchange itself in that lattice. If you want to think of it, this case would be analogous to water by itself, right? It has less different ways it can kind of change its position if you want to think of this as a lattice, because it has only itself in there, so they're identical and indistinguishable particles, the water molecules. So it will end up having a higher vapor pressure, because what's happening is that it wants to, the system's basically looking to maximize entropy, and this allows it to optimize its entropy. We'll get to the optimization of entropy and the second law of thermodynamics in chapter, I believe it's chapter 15. So the bottom line, the thing to note is that the solution, we have the same solvent system in both cases, will have a lower vapor pressure when you have solute particles in it at the same temperature compared to the solvent by itself. So that's one of the colligative effects. And so let's put numbers to it. So if that got you a little confused, don't worry. In chapter 15, we'll get back to it. Just know the big effect is that the solute lowers the vapor pressure of the solvent molecules relative. So let's take two cases, and I'll start out here. I have to keep my hand on the board because it might slip here. So we'll take two types. We're going to study non-volatile, non-electrolyte solute particles. An example of this, a non-volatile, when we say non-volatile, it means it doesn't have a vapor pressure that's appreciable. It's got a very low or basically no vapor pressure. Everything actually has a slight vapor pressure, but it would be negligible compared to the solvent. And this could be something like, example, a typical sugar is like that. So that's good to know. A sugar is effectively a non-electrolyte, meaning it doesn't form a significant population of ions in solutions, and most sugars are very low volatility for all practical purposes, non-volatile for what we're doing here. So sugars would be a typical example of this. Another case that we're going to study is volatile non-electrolytes. This would be species that, again, do not form do not render the medium they're dissolved in to be able to carry a significant electrical current. Volatile here means that they have an appreciable vapor pressure under the temporal conditions of interest. So we're going to use something here. Let's focus on case 1 for this lecture. Case 1 for the non-volatile non-electrolyte solutes like a sugar, what we have is what's called Raoult's law. The vapor pressure of the solution, this is a vapor pressure of the solution, is equal to the mole fraction of the solvent, and we're just going to look at a two-component system, times the vapor pressure of the pure solvent. I'm using the little not symbol here, not to mean standard state. I'm using a little zero symbol or not symbol to represent it's the pure solvent. This could, for example, be water. That's just for example. It doesn't have to be, but I'm going to focus on water. So let's work a problem. At 25 degrees Celsius, the vapor pressure of pure water, and I had to look this up, is approximately 25.76 millimeters of mercury. That's a unit of pressure, just a nice scaling for this type of problem. If we have 1 gram of fructose, actually let me jack that up a little bit. I changed it to get a more appreciable effect. So let me make that 50 grams of fructose, fruit sugar. You can look up this is 186.16 grams per mole. You can verify that yourself. We've done fructose before. 50 grams of it dissolved in 100 milliliters of water. We know that water has a density at this temperature of 0.997 grams per milliliter. I did confirm that's a lot of fructose. I want to have an appreciable effect. Fructose up to about 80 grams will dissolve in water without having any solid forming. So you can still dissolve plenty more in there. Let me just erase on the top so you can see clearly. Continue the calculation up there. So let's do the bit with the moles. If you have 50, you can see 50 grams of fructose do your calculation, can show that that's equal to 0.277. I'm going to keep a couple extra sig figs on here just to, for goodness. We're not justified that many. I just want to keep some extra sig figs on here as we move along. It's extra digits on here as we move along. That's how much 50 grams of fructose is. The water is 100 milliliters. So let's do the calculation for that. I'll actually show that out. 100 milliliters of water times the density is 1 milliliter is 0.997 grams of water. And then we have 18.016 grams of water per 1 mole of water, which equals, let's see here, it's quite a big number. Again, I'm going to keep some extra digits on here. I'm not justified this many sig figs. I'm just doing it so I don't round too early. 5,340 moles. So there's a lot more moles of water. I have to race down here. I'll keep the equation here. We'll just kind of plug in around it. So one of the things we can calculate is the mole fraction of the solvent. Now here is a point where people make a lot of mistakes. For some reason people want to put here the mole fraction of the solute. It's the mole fraction of the solvent when you're using Raoult's law. So this is called Raoult's, and I can't spell if I get this wrong, forgive me, you can look it up. Law. So the vapor pressure of the mole fraction of the solvent, you put the 5.5340 on the top. The moles will cancel. 5.5340. Hopefully I didn't do a little typo here. And then we have 0.27753 moles for the fructose. Verify that. So I end up with 0.95. Let's see here, 22, verify that, it should be very close. So what you do now is just put it in, vapor pressure of the solution. It's going to go down a little bit. This is the solution, vapor pressure. It's going to be 0.9522 times, it has no units. Will you put it in millimeters of mercury? You can convert it to whatever you like. I erased it originally what it was, but let's see what that was. It was 25.76 millimeters of mercury. So the solution for that is 24.53 millimeters of mercury. We're probably only justified to 3 sig figs here. I have to go through it in detail, but the 3 sig figs, that's 25.5 milliliters of mercury. So it's going down a little bit. It went from 27.76 to about 25.5 millimeters of mercury. It's a small drop. I had to actually jack the concentration of the fructose up to have it give something that was not negligible. So this is an example with a non-volatile, non-electrolytic species is sugar. We'll do a volatile non-electrolyte next time. This is a typical example of Raoult's law. You could have something very similar to this on an exam, and there's certainly problems analogous to this in the note sets and in the skill builder set that's independent of notes. And of course, if you have a textbook, there's a dozen problems in there like this as well. And you could take something like this and let chat generate more questions for you if you like this type of problem. So on that note, I'll let you go. Have a good day, and I'll make some more videos tomorrow.